or quadratic surface, we can call it. So if you have a matrix A, then you have a vector x, and okay, so it is like this. You have a column vector x, so let's say x, y, z, and then you have a row vector x, y, z, and this is a matrix here. So what will you have? Okay, let me go back to. See, in the previous case, I have always used 3 by 3 matrices because many things you will miss if you use 2 by 2 matrices. So I went one step above. So I will come back to 2 by 2 matrices. So let me say that I have x, y, and then I have a11, a12, a21, a22, x, y. So what will this be equal to? This is equal to x, y, a11x plus a12y, a21x plus a22y. This is equal to a11x squared, a11x squared plus a12xy plus a21yx plus a22y squared. So this is a quadratic in xy, correct? So whenever we have a quadratic surface can always be written. So anything that you write like this will be an equation of a quadratic surface. Anything that is in the form of a quadratic surface can also be written in this fashion. Okay. Now you will see that if this particular vector is an eigenvector of this A, then what will happen? If this is an eigenvector, then this will be these terms will not be there. So it will be like an isotropic surface. The surface sometimes this is called a stationarity property. This quadratic surface is stationary along the directions of the eigenvectors. See, do you realize that you have, for example, in classical mechanics, you will come across this kind of quadratic surfaces when you deal with what is called equilibrium oscillations of near equilibrium oscillations, or small oscillations. So if you have an equilibrium point which slightly displays from the small oscillations, the dynamics are governed by the harmonic oscillator potential. So you will write the Lagrangian as half. So you write, for example, x dot, y dot into a matrix, x dot, y dot. This is the kinetic energy. This matrix will involve mass, etc., plus half x, y into a matrix x, y. So this matrix, you call it as potential energy matrix. This matrix, you call it as kinetic energy matrix. And you might recall that you ask v minus omega square t determinant is equal to 0 to find the normal modes of vibration. Okay, so this is the quadratic form that you will use. So there we know kinetic energy and potential energy expressions, and we are using this construction of quadratic forms to get these matrices or the linear transformations through which we can find normal modes. But if you know some linear transformation, you can also write down a quadratic form so that some geometric properties of the quadratic forms can be discussed by construction of quadratic. There is another context in classical mechanics where quadratic forms are important is if you have a rigid body dynamics or rotational dynamics, moment of inertia tensor is a matrix, and the kinetic energy of this is given by omega x omega y into omega x omega y omega z into half this. This is called, you write it in this way, half omega t I omega transpose. This is called, and this is rho. So this is called the rotational kinetic energy. Rotational kinetic energy of the rigid body is also a quadratic form of momentum inertia. So
Hamiltonian dynamics usually is quadratic forms for the Hamiltonian as square terms,
yeah,
square and two square terms.
yeah.
This is also called quadratic form, but there is no cross term in the number.
Basically, when you say quadratic Hamiltonian, it is not necessarily only x square and p square. It can have x, y, and px also, because you can always make a transformation and write this as some other capital X square plus capital P square. So quadratic essentially means x square or p square or xp or px. So together, the power together should be equal to 2. The cross terms are also available. What I am saying is, if cross terms are there in the Hamiltonian, you can always discover a canonical transformation to remove those cross terms in the new coordinates. That is possible. So that is only the form of the Hamiltonian in this particular position momentum coordinates. So this is called the quadratic form.